What is magnetic permeability in electrical engineering? Imagine a magnetic field trying to pass through different materials. Some materials let it flow easily, while others resist it strongly. That's where magnetic permeability comes into play. It's a property that tells us how easily a material can support the formation of a magnetic field inside itself when an external magnetic field is applied. Think of it as how well a material can become magnetized or how freely magnetic field lines can pass through it. This idea is fundamental in electrical engineering because it influences how devices like transformers, inductors, and electric motors work. Magnetic permeability is defined as the ratio of the magnetic flux density inside a material to the magnetic field strength applied to it. The magnetic flux density, often called B, measures how much magnetic field passes through a given area. The magnetic field strength, called H, is the intensity of the magnetic field applied. The formula for permeability is μ equals B divided by H. The unit for permeability in the International System of Units is Henries per meter. It helps engineers understand how different materials respond to magnetic fields. Materials are grouped based on their permeability. High permeability materials, like iron and certain steels, allow magnetic fields to pass through easily. These materials are used in the cores of transformers and electric motors to concentrate and guide magnetic flux. Low permeability materials, such as air or vacuum, resist magnetic field formation. The permeability of free space, which is the permeability of a vacuum, is a constant with a value of about 1.2566 times 10 to the minus 6th henries per meter. This value acts as a baseline for comparing other materials. There are two main types of permeability: absolute permeability and relative permeability. Absolute permeability is the actual permeability of a specific material. Relative permeability compares a material's permeability to that of free space. It is calculated by dividing the absolute permeability by the permeability of free space. Relative permeability is a number without units that shows how much more or less permeable a material is compared to a vacuum. Several factors influence a material's permeability. The strength of the magnetic field, the temperature, the frequency of alternating fields, and the material's position within the magnetic field all matter. For example, ferromagnetic materials like iron can change their permeability depending on how strong the magnetic field is. They often show a nonlinear relationship, meaning their permeability can increase or decrease as the magnetic field changes. In the context of Faraday's law and electromagnetism, magnetic permeability is key to understanding how much magnetic flux links with a circuit. When magnetic flux changes, it induces an electromotive force or voltage. The permeability of the core material affects how much flux can be linked and how effectively a device like a transformer can operate. High permeability materials help maximize flux linkage and reduce energy losses, making devices more efficient. Permeability also plays a role in shielding applications. Materials with very high permeability can redirect magnetic fields away from sensitive electronic parts, protecting them from interference. This is especially useful in environments with strong magnetic noise. To sum up, magnetic permeability measures how easily a material can support a magnetic field. It influences how magnetic flux is generated, controlled, and used in electrical devices. Whether designing transformers or shielding sensitive electronics, understanding permeability helps engineers create better, more efficient systems.